We've been talking about how magnetic fields affect moving charges or the forces they exert on wires. Excuse me. But it turns out you can produce magnetic fields by having moving charges or currents in wires. And so this is the first time we'll look at how a magnetic field gets produced. And so currents in wires produce magnetic fields around the wire. And we'll talk about what that looks like in a second. In this equation, we're just going to say, look, the magnetic field near a long straight wire carrying current I. And so if I just have a long wire, like say this one, and it's carrying a current I in it, it produces a magnetic field around the wire. And I'll draw a picture of that in a second. The formula for the magnetic field is B equals mu naught I over 2 pi r. Mu naught is the magnetic permeability of free space. It's like a magnetic version of epsilon naught. If you remember, epsilon naught was 1 over 4 pi k, or like 8.85 times 10 to the minus 12th coulomb squared per newton meter squared. Mu naught is 4 pi times 10 to the minus 7th Tesla meter per ampere. Right? If you work this out, if that's mu naught, you multiply it by amperes and divide by meters, and you get Tesla, which is what the magnetic field is. I is the current in the wire, and R is the distance from the wire. And so I'll do an example here in a second where we'll also talk about, well, what's the direction of the magnetic field? So in this problem it says how far from the starter cable of a car carrying 150 amps, so the starter cable is carrying 150 amps, is the magnetic field less than the Earth's, which is about 5 times 10 to the minus 5th Tesla, right? And so if we assume the wire is straight, then this formula applies. Right? But now they're asking us for this, and they're giving us everything else. And so if we rearrange this formula, we get R is equal to mu naught I over 2 pi times the magnetic field. And we know all these. This is 4 pi times 10 to the minus 12th, times 10 to the minus 7 Tesla meters per ampere times 150 amps. 150 amps. Made a valiant try at that. Divided by 2 pi times the magnetic field, which is 5 times 10 to the minus 5th Tesla. Right? And so if I work all that out, I get about 0.6 meters. So we can now ask the question, well, what's the direction of the field near the wire, right? And this is the second right-hand rule, right? The first one was, how do you calculate the direction of the force in the Lorentz force? You point your arms in the direction of the velocity or the current, curl towards the magnetic field, and your thumb points in the direction of the force, right? This is the right-hand rule that allows you to calculate the direction of the magnetic field near a wire that's carrying current. And so point your thumb along the current. And so if this is my wire here, say that's my wire. I don't know if I can do this. Maybe I can do this. Right? If that's my wire and the current's going that way, then I point my thumb in the direction of the wire like this, and then I curl my fingers around the wire for the direction of the magnetic field. So the magnetic field goes around the wire like this in loops. And so to be more clear for this wire, just under the wire where my hand is, the magnetic field is pointing that way, right? And then on top of the wire, it's pointing back the other way, right? The way my middle finger is pointing right now. On this side of the wire, it's pointing up towards you, towards the camera. And on this side, side closest to me, it's pointing down. It's just making a circle all the way around the wire, and it's just pointing tangent to the circle at any point. Down on this side, towards the top of the screen on this side, up on this side, and back down on this side, and so on. And so it makes little loops around the wire that look like that. That's the second right-hand rule. You point your thumb in the direction of the current, and you curl your fingers in the direction of the field. And so they should give you the direction at any point. So now I can ask the question, two parallel wires a distance r apart, right? These are two parallel wires carrying current in the same direction. One carries I and the other one carries I prime. They're both going the same way. And it says, what forces do they exert on each other, right? Magnitude and direction. And so remember, a magnetic field, right? The Lorentz force as a magnetic field produces a force on a wire. It's ILB sine theta, right? And so if there's a magnetic field around this wire, it's carrying current I, then it's going to exert a force. Well, from the last section, we saw that there in fact is a magnetic field near this wire due to this wire, right? A wire carrying current I produces a magnetic field around it like this, right? And so I could say the magnetic field due to this wire is B prime is equal to mu naught I prime over 2 pi r, right? That's the magnetic field due to this wire a distance r away, so where this wire is, right? It's the magnetic field due to this wire. And so I would say, look, the force on this wire due to this magnetic field, I would just put a prime there. And we'd have to figure out the direction, right? The direction, the theta, is the angle between B and the direction of the current. And so we have to use the second right-hand rule to figure out the direction. And if we can imagine that we're curling our fingers around this wire here, right? Above the wire, the magnetic field is going to point out of the board. That is to say, where the wire carrying current I is, this is magnetic field B prime. It's the magnetic field due to this wire, where this wire is, right? It's coming up out of the page, right where this wire is. And so I could say, look, the force due to I on I prime, that is to say, due to I prime, the force due to this wire on this wire, I'll get it right in a second, right, is equal to just what I wrote up here. IL B prime. And since the current is that way and the magnetic field is this way, they're at 90 degrees, the sine of theta is just 1. And so this gives me IL, and then B prime is mu naught I prime over 2 pi r. And notice if I want to figure out the direction of the force, remember I have to use the first right-hand rule. And so my current's going this way, my magnetic field is going up. And so the force on this wire, F due to I prime on I, is down, right? If the current is this way and the magnetic field is up, then I have a downward force, right? Similarly, I could say, look, what's the direction of the magnetic field due to this guy down here? Well, this guy, I may have to turn my body a little bit. This guy's current is this way, and so I's current is this way. And so if I put my thumb that way, my fingers are pointing down where I prime is. Or I could do it this way, and I can say, look, on this side of the wire, here's my thumb pointing in the direction of I. On this side where my fingertips are, it's pointing down. And so I'd say, look, B points this way. B prime up here points out of the board, but B down here points into the board. And so I could say, look, the force, the force, one more time, the force due to I on I prime is just I prime L B. That is to say, the current through this guy times the length of the wire times the magnetic field due to this guy down here, right? And that's just I prime L, and this guy's magnetic field is just mu naught I over 2 pi r. Notice these two come out the same. That is to say, the force due to I prime on I and the force due to I on I prime are both equal to mu naught L. You know, if I wanted to write them a little more succinctly, I could say mu naught L I prime over 2 pi r, if I wanted to gather the terms a little bit. Both of these things would be equal. And that's what we expect, because they're exerting forces on each other, and Newton's third law says the forces should be equal. It also says they should be opposite, which means that the force due to I on I prime, F I prime, has to be the other way, right? And you can see that it is. The current is going this way, the magnetic field is going into the board, and so this guy gets pushed that way, right? And so the top wire, right, it gets pushed this way, the bottom wire gets pushed that way, and they're attracted to each other. And all we need to know is the length and the currents and the separation to figure out what the force is. So in this problem, I have two parallel wires, each carrying 200 amps and 2 meters apart. What's the force per unit length between the wires? And so in the last problem we showed, in the last section we showed that the force between the wires is mu naught L I prime over 2 pi r, right? And this was for either wire. They came out the same, and they attracted each other if they were in the same direction. You should convince yourself maybe that if they're carrying current in opposite directions, they repel each other. That's just the second right-hand rule. See if you can convince yourself of that. If they carry currents in opposite directions, they repel. If they carry current in the same direction, they attract. But this question is just asking me for the force per unit length, and so they're asking me for F over L, right? And so that's equal to mu naught I prime over 2 pi r, right? And so that's a bit of a mouthful. It's 4 pi times 10 to the minus 7 Tesla meters per ampere times 200 amps squared, because both I and I prime are 200 amps, divided by 2 pi times 2 meters, right? And so if I evaluate this, I'm getting there. I get 4 times 10 to the minus 3 newtons per meter. Wires carrying large currents that aren't too far apart can attract each other. This is a small force, but it's for every meter of wire, and so they can have a small effect on each other.